Welcome, everyone, to this Professional Development Hour presentation brought to you proudly by the Atlanta Metro Chapter of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. Before we begin, we'd like to let you know that any opinions presented tonight are solely the opinions of the presenter and not that of the Georgia Society of Professional Engineers, the National Society of Professional Engineers, or any other of its affiliates. We certainly hope you will enjoy tonight's presentation, so sit back and relax. And on with the show.
Very good. Let's get going then. Okay, the name of the presentation today is the Professional Engineers Coexistence with Artificial Intelligence and Machine Learning. Our speaker today is J.P. Halliwell. He is a graduate in electrical engineering from Auburn University, master's in electrical computer engineering from Georgia Tech. He is the president-elect of the state chapter, Georgia Society of Professional Engineers. So I'd like to please join me in giving JP a warm welcome.
Thank you, Jesus. I am very excited to be here today. This is my first, like I said, time coming to the Atlanta Metro Chapter, even though I probably belong to the Atlanta Metro Chapter and therefore should be here more often. As Jesus said, my name is J.P. Halliwell. This is a reprise of a talk that I gave at the National Society of Professional Engineers Conference last year. Same title, more or less the same content. The bulk of the subject matter is effectively... my goal was effectively to start a discourse between how the professional engineer could coexist with artificial intelligence and machine learning, especially as those technologies become infinitely more deployable and infinitely more available to more and more varied levels of technical personnel, is the way that I'll phrase it. One of the ways that I like to summarize this is that what it really boils down to is, I'm sure that we've all been on Wikipedia at some point for a very complicated topic. We've read the first paragraph and gone, yeah, okay, I understand that. We've read the second paragraph and go, okay, that's starting to get a little fuzzy, and then that third paragraph is just noise. And somehow it completely degenerates into abstract topics that are so far beyond your level of understanding that even getting to that third paragraph, even trying to understand that third paragraph would be this monumental thing, maybe involving a 4-year degree or something like that. My goal is basically to my goal with this conversation is more or less to allow for you maybe to get to that third paragraph and beyond, just by exposing you to the terminology in a more digestible fashion, as well as just a broad discussion of I'm sure that there are a lot of managers in the room who don't care what AI is, they just care how their engineers can use it, and more or less talk to that a little bit as well. As Jesus said, these are my credentials. I'm a systems engineer with the Georgia Tech Research Institute. I've been fully employed with them since 2014, but I did my co-op with them in 2012. So, rough order of magnitude, that gives me about a decade of experience with Georgia Tech Research Institute. I'm the president-elect of the Georgia Society. It is my honor. Mitch is my president. I've been really enjoying working with him, and I hope that I'm able to serve you better in the upcoming couple years as I'm on the executive board. And I have a focus on what I describe as the design, the test, and delivery of safety-critical embedded software applications predominantly. If that sounds like a bunch of mumbo-jumbo, you can understand it to be things that if they fail, very bad things happen, and how do we stop them from failing them in a deterministic fashion, right? Stopping failures in a deterministic fashion. And hopefully you identify with that as kind of the core of what professional engineering is. How do we not let things fail in a way that it aligns with our science? Starting with an understanding of AI and ML, I always like to ask the question, when you think of AI in pop culture, what do you think of? And this is a genuine question. I'll take hands to shout it out. What do you think of when you think of AI in terms of pop culture? HAL is a great one. What else? Any others?
ChatGPT.
ChatGPT is a great one. Terminator, great. So having said a few of those, what in general in pop culture is humanity's disposition towards those AI, and what is AI's disposition towards humanity in those items of pop culture. And overall, it's pretty negative, right? We tend in pop culture to have a somewhat negative opinion of AI, and perhaps it's not necessarily unfounded at this point in time. Obviously, we said Hal from 2001: A Space Odyssey, a book from I don't know when, but a movie from the 60s, 70s era, 70s, I think, pretty confidently. Naturally, we have C-3PO and R2-D2. I'm sure that the true Star Wars files would argue, well, they're not AI, they're droids, and those are different. But functionally speaking, from the aspects of what we see them do in the course of the movies, I think it's safe to categorize them, technically speaking, as AI, at least to we humans in a galaxy here today. We have Terminator. Well, we have Skynet and we have Terminator. Skynet being the overall brains behind the machines in the Terminator series. And more recently still, we have Ultron and Vision from the Avengers movies. And in this case, we have a positive and a negative example. This is one of the few positive examples of AI that I could find in pop culture recently, at least as far as movies go. So given what we sort of have been exposed to with AI in pop culture, what do you think AI actually is? If you had to put a pen to paper definition of AI, what would it be? And say that again? Sure. It's tough. It doesn't really. I know what it isn't. I know that it's a very bad robot that's traveling through time to come and get me, but that isn't really what AI is. And more complicated still, what do you think machine learning is? We can't point to something and say that's machine learning, but I can point to something and say, well, that's AI. And I hope that at the end of this talk, maybe your opinions of that has changed. This is one of the.
Am I wrong to think it's zeros and ones?
Sort of. Very many zeros and ones is I think, a fair description. This, to me, is one of the most evocative, illustrative Venn diagrams I've seen in my course of AI research, AI and ML research. What you can note here is that AI is the very huge, we'll call it blue circle. Machine learning is a somewhat smaller yellow circle. Deep learning is a subset still of machine learning. And then there's this entirely different fourth circle called data science, which is sort of overlapping with those previous three, but is in and of itself is a very, very complex subject. AI we can really classify as just a computer engaging in learning. I think that it's very easy for us as humans to know what learning is. That you can expose someone to something, a complex topic. They don't understand it today, but they're becoming familiar, and then sometime in the future they know it. They've learned it, whatever it is, whether it's a skill, whether it's a technique, whether it's just a trivia fact, right? Like who won the 1972 Super Bowl? Someone learned that. Someone learned that on the day that the Super Bowl aired 50 years ago. What that means is that AI also comprises machine learning. It comprises computer vision. It comprises natural language processing. We'll talk about what those are in a little bit more detail shortly, but machine learning is an AI technique that's traditionally used in concert with categorical data for classification and anomaly detection. If any of you have watched the show Silicon Valley, there's a great scene wherein they develop a machine learning model that can identify whether something is or isn't a hot dog. That's all that it does. It tells you that it is a hot dog or it isn't a hot dog. And that's effectively what machine learning is very good and very capable of doing, is identifying a Boolean, yes it is something or no it isn't something. More advanced machine learning models can do more than Boolean. We'll call it multi-axis, but maybe they can identify a cat or a dog or nothing, we'll say. The very brief version of the terminologies that I'll introduce here are what I would consider the high notes. Training is like the de facto standard of what AI and ML are being utilized for. There's a ton of different varieties of training, but fundamentally the training is how you are teaching the AI or the ML to behave in the way that you want it to behave. If you're teaching it to identify a hot dog, well, you'll show it a ton of pictures of hot dogs. If you're teaching it to not identify a hot dog, you'll show it a ton of pictures of not hot dogs, whatever that is. And ultimately, as you run through the algorithms that are generating these models, the AI or the ML will become better and better and better as your data, especially, is your limiting factor. I mean, how many pictures can you provide to me of hot dogs?
how I heard is that they teach it's not hot dog, but it's a bratwurst or something like that.
Difficult, but perhaps not impossible. Especially with nuances such as those. The question is, how difficult is it to select between different types of sausages? I guess we'll broadly define it as. And the short version is, if a human can detect it, chances are we can teach an AI or an ML to detect it. So perhaps there's sausage sommeliers who can identify at a glance the difference between a bratwurst and a so-and-so, but I know I can't, so maybe that exists as well. I do know that there are ML models that can identify dog breeds very, very accurately. And so they'll be able to say, well, that's a Rottweiler versus a German Shepherd versus a Dachshund, and they're very accurate. It's very easy for me to say, well, that's a dog. I don't know what kind of dog it is, but it's a dog. Validation naturally is the second step after training, and this is actually testing that your model is performing in the way that makes sense. Training and validation are going to be happening many, many times. These are things that are happening at the speed of computers today. So you might have a model that's on its 2000th generation of training and validation, just trying to seek that incrementally better improvement as your model gets more mature. Testing is what within the machine learning pipeline of so to speak development. You won't use all of your data to train your model, and the reason for that is because there's a concept known as overfitting, this last bullet point, which basically means that you've developed a machine learning model or an AI model that is overtuned to only the data that you've input into it. And so if you have 1 million pictures of hot dogs that you blast into your model, it'll identify every single one of those pictures perfectly well. And then you show it that millionth and first picture, and it won't be able to detect it because it's not actually detecting the hot dog, it's detecting almost metadata, if you want to call it that, data about the data. So testing is when you're actually using a portion of your data as new, untested, untrained information against your model to verify the model's behavior. Overfitting is a huge problem. You can think of it as a form of bias that models can have. There's a lot of literature about the appropriate ratio of data to use for training versus testing. The standard rule of thumb is 80-20, but depending on the models that you're using, that number can float. We talked briefly about learning and about training. Those fall into two major camps. The first is supervised learning, and the second is unsupervised learning. Supervised learning sort of gives the impression that a human is sitting down in front of the computer and seeing what the model does and is agreeing with it, and that's not necessarily true. Typically what this means is that a human or some other device has come through the data and actually labeled the data. So it's gone through all 1 million of your pictures and said, this is a hot dog, this isn't a hot dog, this is a hot dog, this isn't a hot dog. Supervised data is very easy to implement, but obviously it requires time for a human to actually go through all of your data and actually verify that all of your data is labeled correctly, because improperly labeled data is catastrophic to AI development. Catastrophic may be a little extreme within this room, but it's bad enough to really tank your model performance. Unsupervised learning is the opposite. It's training except without labeled data. So this is you downloading 1 million pictures and training it, and you don't care about learning or about categorizing the data or labeling the data. There are models that really benefit from unsupervised learning, but generally speaking, it's a lot more difficult to deploy something involving unsupervised learning for the purposes that it's hard to detect. Ultimately, a human being has to evaluate the model's performance, and if you don't know if you yourself don't even know what the data holds, it's tough to know how well the model is behaving. That's a simple matter of arithmetic. Computer vision is actually teaching a computer to see. So, unlike this projector, which is sort of seeing a picture coming out of my computer and putting it up on the screen, it's not really seeing the picture. It's effectively doing a digital handshake of taking something from the left and moving it over to the right. Computer vision is actually teaching, for example, a car to have a video stream and to recognize objects within that dynamically changing, unpredictable video stream. This computer vision is also, for example, teaching a computer to read handwriting, just any arbitrary penmanship. It's a very, very powerful tool, not even for self-driving cars, but just for, within my world, every now and again we'll come across documents that were typewritten in the 70s or 80s or so, and we'll scan them in, and they're a real pain in the butt once they're digitized because you can't find through them. You have to scroll through them manually. Well, optical character recognition, which is a subset of computer vision, can actually scan that document with a computer's eyeballs and turn that into a digitized copy that is actually data instead of just pictures of letters. Natural language processing, I think that I've briefly mentioned, but if computer vision is a computer seeing, natural language processing is a computer speaking. This isn't necessarily producing actual audio corresponding to human languages, but perhaps reading it, writing it, etc. Natural language processing, I was talking with Phil, is, I think, very, very easy to demonstrate within the confines of ChatGPT, if any of you have played it. You enter an arbitrarily complex question in human English, and it gives you an arbitrarily complex response in human English, in perfectly formatted human English. The data within might not be right, the answer might not be correct, but dang it, that English is right. And as a construct of NLP, that is bewildering to me, the level of fidelity that they've achieved with that model, just in spitting out good English. Natural language processing is particularly complex because the way that humans communicate with each other, the way that I'm communicating with you in this room, is highly mutable. It changes even on a day-to-day basis. We're constantly creating new words, new ideas, new concepts to communicate to one another. But also we're really wasteful with the way that we communicate. Probably 60% of the words that I've spoken through the course of this presentation haven't really added any value to the presentation. They're just words that we've decided follow some rules, and they're better to somewhat communicate ideas better, but you probably don't need prepositions. Any of them. Of, by, from. You can probably communicate 90% of a sentence without any prepositions, just by context, understanding, etc. Computers are very good at throwing away prepositions. Computers are very good at bad natural language processing. They're not good at great natural language processing. There's a couple other topics that I list down here in the final bullet. Active learning, generative adversarial networks, reinforcement learning. These are, I won't talk broadly about these, but you should know that there are, with AI being the next frontier, so to speak, of research, there are a lot of different terminologies that are coming up. Ultimately, you can reduce them down into certain flavors, is the word that I like to use to describe it. I think the real one to highlight here are generative adversarial networks, GANs as they're called. General adversarial networks are capable of creating data that is representative of its original data, but isn't quite the same. So, for example, deepfake videos are using generative adversarial networks to create things that look like humans, but probably aren't actually humans that exist. These are effectively pictures of people that we look at and we say, that's a person, when in reality it's just a picture that a computer came up with that could fool 99% of people into believing that it's a picture of a real person. GANs are super powerful, not just for, we'll call it disinformation, but also for, I've seen GANs used for projects that have very limited data by which to train ML or AI. They use a GAN on the data that they have to generate data that looks kind of close to the data that they want to train on, just to get more data, and then build an ML model to that. It's an extremely powerful tool, if not somewhat worrisome, I'll say. That's my very brief 7-slide understanding of AI/ML. Like I said, I hope that at least gets you to that third Wikipedia paragraph, maybe the fourth. But fundamentally, the underlying concepts behind all of this is math, pen-to-paper math. And without understanding the math, obviously, it's tough to really get into the nitty-gritty of what's happening behind the scenes, but the terminology is appropriate nonetheless. Yes?
A lot of this
teaching the models to learn depends on the data, right?
Naturally.
So somebody has to spend a whole bunch of time going through the data and cleaning it up. Is that happening, or we should be able to be in it? Because in my experience, I have a problem, which is a distribution network optimization. How many distribution centers do I place? Where do I place them? All this. That's driven by a lot of shipment and transportation data.
Yep.
Every time I plan my project, my plan is to spend maybe 30% looking at the data. I invariably end up spending 80%, and then the analysis kind of gets cut off.
Sure.
So, and it's not a consistent issue.
Of course.
Right? If I find an issue here with client ABC, it's going to be totally different with client X.
Of course.
So how do you do that?
Monumentally. The effort involved in not only collecting the data, but in parsing the data, what's known as data massaging, taking the data that's the scrubbing, is a monumental effort, and that's why a lot of the big tech companies have distributed it out to you. Whether you know it or not, you're contributing to their data collection, if not their data scrubbing. Every time you log into a website and you get that little thing to select the squares that have buses or bicycles or whatever, Google most likely is using that information to train its algorithms, to train its models. You as a human being are very quick at saying, well, there's no bicycle there and there's a bicycle there, click. Computers don't have that. There's no circuit that is a bicycle detection circuit, right? We have to train very complex models that we don't even really fully understand once they're created. We understand the math that created them, but maybe not the output that is running fundamentally. The data processing is a monumental task, and it's really the life or death of a successful AI deployment, in my opinion. It's no joke. And the best part is when you get folks who say, oh yeah, we have a great data set. And the amount of data may be great. The quality of the data is invariably poor. Yes?
Tesla came out with their main car that people knew around 2012, 2013. They predicted they'd have full self-driving by 2015. They really don't quite have it yet. Mm-hmm. It has proven much, much more difficult
Absolutely.
than was ever anticipated.
Absolutely.
I was involved in a project with Brown-Boveri converting the Westinghouse computer system to interface with the 26 different mainframes at different factories. They ended up kind of incorporating the airline industry when they had a mainframe computer to the mainframe of the system to interface to the communication coming in and out to place an order.
Yep, sounds about right. And I think that eventually we'll reach a point where it is going to be AI the whole way down. We'll have some AI that is creating data to train some other AI that is using data to train some other AI that is using data to train some other AI. In broad strokes, we'll just call that the product. Whatever that product is actually doing. It'll be nested AI, if you want to call it that, or at least nested ML for sure. Yes, Roger?
Would you comment on the term fuzzy logic?
Sure. Yeah. So within computer science, naturally computers we're taught a Boolean. They interpret zeros and ones, and that's a lot of times because of the circuitry that we're using is capable of transmitting two voltage levels. We'll call it a zero or we'll call it 5 volts, but the voltage level ultimately doesn't matter. Zero and not zero. Computers, traditionally being Boolean, we learn Boolean logic. We learn A and B. We learn that 1 and 1 is 1. We learn that 0 and 1 is 0. Fuzzy logic is sort of a succinct way of putting it would be almost as if we were dealing with analog Boolean logic, where there is such a thing as a 0.5. And what the 0.5 means isn't necessarily a voltage level. It isn't necessarily an actual definitive no answer. It's just another value that can be categorized. I thought about I read a paper at one point, I don't remember who it was, but I think that they developed a ternary system, a ternary computer that actually had three levels. And it worked okay, but ultimately I think the circuitry was too expensive to make it supplant binary computing, even though if we could add 50% more states to all of our data at this point, to all of our computers at this point, our processing power would go through the roof, invariably. And if we had quadrinary, if we had four states in all of our circuits, we'd have crazy computers tomorrow, by today's technology at least. This next block of slides, I talk about current AI and ML jobs, I guess. A very, very hot button topic in at least private industry is predictive maintenance. You can think about this as if you have a human being or eventually a drone walking around with a camera and just recording some system that based off of the training data and based off of the years and years of maintenance that you've had to perform on very static systems, that you'd be able to train a model to say that tire is going to fail in 3 flights, that tire is going to fail in 50 miles, that bolt is going to fail in 20 days. There's certain rules that can be followed based off of what humans do. I mean, I look at that tire and I, as a non-expert, say, I don't think it's supposed to look like that. But what if we could detect that 3 weeks before that damage had actually happened, using a model that was able to, in fine resolution, detect this sort of failure as it's starting, that maybe is beyond the limitations of what humans can really detect in the moment, at least. You could further improve the maintenance, for example, by introducing other data, such as in the case of this landing gear, right? If it's a transatlantic flight that's only landing twice a day, maybe, it's going to experience a lot fewer landings and takeoffs than something that's traveling back and forth to Boston 12 times a day. I don't know if that's a realistic number, but figuratively speaking, if it has an order of magnitude higher landings per day, the tires are going to get that much more wear on them, and so it's a lot easier to correlate that. But similarly, maybe the overseas flights are heavier, and maybe that wears tires out significantly more, and so those sorts of things are data that aren't necessarily directly relevant to tire maintenance, tire wear, but maybe they are relevant to predicting tire failure.
Different weather conditions.
Of course. Right. Right. I'm assuming that the airports that are out in Death Valley are very, very rough on their tires by comparison to the ones that are out in Juneau. Documentation scraping is another very, very effective workflow utilizing AI and ML. This is using NLP to sort of identify the semantics in large sets of documentation. Twitter, Facebook, Google are doing this on everything that they're able to scrape. Twitter, people are just willingly submitting information to them with every tweet. Why not scrape that? Why not see if you can train a model based off of the troves of colloquial English or colloquial whatever language it may be that's being posted to Twitter, right? Like, if you were doing only an analysis on every book that's ever been published, you would get a very different NLP model than one that's actually combing pop culture and combing very colloquial English, and it may be better in certain scenarios. It may be worse. If you're trying to create a model that can detect plagiarism in academic papers, maybe you want the one that's been trained on books. But if you're trying to create a chatbot, something that sounds like it's a real human on the other end, probably that one that is going to sound a little too academic, maybe a little too hoity-toity to really sound like a real person. This is an example that we came across when we were preparing these slides of a review for, I don't remember which Toy Story movie it is, but it's the exact same review, you probably can't tell from the screen, posted by 2 different individuals. And the first thought is, well, why? Right? Like, obviously it's a fake review, but why is there this fake review in existence? And it could very well be that someone's just training a data set, training a model, training something for an alternative purpose, and they go, well, if I can make fake movie reviews, maybe I can make fake something else. Briefly talking about the process of actually deploying a model, the first step is data. You can't train a model without data. You can't even begin to think about working with AI until you've identified what data you need to get. Acquiring the data, sometimes that's very difficult. Sometimes it's very easy. NIST, N-I-S-T, an acronym that I can't remember the name of, but is a National Institute for Science and Technology. Great. They have a ton of data sets that are just freely available for you to do whatever you want with them. They range from words, they range from pictures. There's a whole lot of things that you can do with them. So a lot of, especially introductory AI and ML courses will actually baseline a lot of their stuff off of the availability of these NIST data sets. And it's very easy to see the ways, it's almost in certain circles it's become a little bit of a competition. You use this very well-known data set to try to achieve better and better performance, and that's sort of the benchmark for your new ML algorithm or AI or whatever it may be, is using this very clean, very benchmarked data set. Pre-processing the data, as Jesus said, sometimes this is a monumental effort. Sometimes this is unbelievably difficult compared to the level of effort that you actually want to engage in this model. Labeling the data, if you're using supervised learning, obviously you have to label the data. If you're doing unsupervised learning, you still need to have some labeling that a human can understand to actually verify the model's performance. In this case, we have sort of a joke. Acquire, you Google pictures of bridges. In step 2, well, you turn your blurry pictures of bridges into sharper, better understandable pictures of bridges. And the third one, you say, okay, well, that's the Tower Bridge. That's the Golden Gate Bridge. Or that's a suspension bridge. Whatever you're actually trying to train the ML for would be what you would label your data as. So if you're trying to label it as a big bridge or a small bridge, maybe a human being can look at it and say, well, that's a big bridge, that's a small bridge, whatever the actual arbitrary distinction is between a big bridge and a small bridge. As far as actually training the model goes, this diagram will start on the left-hand side. It shows up purple on my screen, but I'll call it gray. The gray cylinder is data. You feed that into the actual training portion. There's a square below it that says validate, and after the model is training, it goes through the validation step where it sends its predictions to the validator, and the validator computes an error. The error is what is iterated upon. You're trying to minimize the error, obviously, because high error means that you've got a bad model, and low error either means that you have an overfit model or it means you have a good model, and that's up to a human to really differentiate. Following validation, it'll go to test. Testing is more or less the same step that happens during validation, except you're not generating an error from your test step, whereas with the validation step you are. Finally, there's what's known as the delivery. Broad strokes, in the commercial world, delivery means that you're deploying your model to the cloud, whether it's your Google Assistant or Siri or whatever that you're constantly at your fingertips. That's living in the cloud somewhere. That's delivery. And then when you retrain, you grab your latest model from the cloud and repeat the process all over again. You can understand the cloud in this case to end up being the target within going to end up using the model. Like I said, broad strokes in the commercial world, invariably that's the cloud, but there's no reason why it can't be a laptop or some other device such as that. I won't talk very deeply about this slide, but within the community there's a concept known as MLOps, machine learning operations. That is the process by which machine learning models are constantly trained and deployed in a very, very quick and rapid fashion. So everything to the left of the orange dashed box is more or less the data processing, gathering the data, cleaning the data, and gathering the data, cleaning the data, and storing the clean data in a place where your model can get it to be trained on. And then everything within the orange boxes, a more in-depth version of the chart that we saw on the last slide, wherein the model is trained, validated, and tested, and ultimately deployed and repeated. I would be surprised if there aren't actually open positions on Indeed or anything like that for MLOps engineers, people that would work within this sector, just refining the pipeline, not actually doing the model development themselves, not modifying the algorithms, not modifying anything that actually is used as an input to the product, but just maintaining the pipeline, just maintaining the infrastructure required for this to happen. That leads us to, well, what does it mean to deliver? Ultimately, it just means you get your model to the customer. Is the customer 6 billion people with an iPhone? Okay, that's a slightly different problem than the state who's going to have it on a few laptops while they're doing predictive maintenance on roadways or whatever it may be. But ultimately, it also alludes to the infrastructure that's required for continuous delivery of that model. The worst thing you can have is an outdated model. The ability of software to be soft, to be changed, is something that should be leveraged, especially in the case of AI and machine learning development. And ultimately that leads me to, well, where do we fit in? Where do we as professional engineers fit into that? If we're going to have something that's constantly changing, that's going to be constantly used, whether it's to generate effectively blueprints for a design, or just to actually create the design completely, in 100 years from now when we have fancy robots that are capable of deploying public works completely autonomously, and a human being just has to say, yep, go ahead. Where do PEs fit in? And that's an answer that I don't have the question to. I've been a professional engineer for 5 years. I've been doing AI and ML research for about that long. I don't really know. This next slide, I hope, is sort of evocative there, right? Like, well, is a PE responsible for gathering the data? Is a PE responsible for cleaning the data? Ultimately, what's noticed is that these AI technologies and its machine learning models are highly subject to bias. And so, if we're able to introduce biased data into a system, the model could behave in ways that are in an unintended fashion. Well, does that mean that we need a professional engineer, just a data engineer? Is that the new license that's going to come out? Is you're a PE and what you focus on is data engineering, and what you do is verify that your data sets aren't biased, that they aren't incomplete, that they're labeled correctly. How do you apply a stamp to a data set? I don't know that. I mean, I don't. We haven't even talked about the machine learning operations side of things yet. All we've talked about is the stuff to the left. As a professional engineer responsible for the validation, for the training, for the deployment, for the delivery. I mean, how many PEs do we need? Is this just one professional engineer that's fully invested in every step of this project, or do we need a professional engineer for each one of these pieces? I don't know the answer to that. But
should we not use an AI to validate the previous output?
Sure.
Review data, this would be the same answer.
Sure, you could. But has a PE signed off on that AI? And I guess that's ultimately what it boils down to, is that I don't have a good answer for at what point trust is implicit. When a PE certifies the designs for a bridge, he's assuming responsibility for every component on that bridge, down to the very last screw, we'll call it. I don't know how that works similarly for AI and ML. Yes?
It comes down to something very similar in classical software development, and that is the question that is asked, when are you finished testing?
Right.
Previously, I worked for a company that made infusion pumps for use in hospitals. They had the devices had a large amount of software that was built into them. And we always wrestled with the question is, when are we finished testing? Well, the FDA had a very simple answer to that. If you've detected a bug, you have to either prove that the bug does not affect the operation of your device, or you have to go and fix it. So it always was easier to actually go and fix the bug than it was to prove that it was actually denied. So, with AI, you've got something very, very similar to that. It's just you don't have anybody who's really in charge, because it's the AI, it's the programming itself that is doing that.
Absolutely. Very succinct. I really like that. That all leads me to the last section of this presentation, which I've called PEs and the Trust of Intelligent Systems. I like to start it off with the question, how does the public know today, June the 12th or whatever it is, to trust engineering developments? If we asked anybody that wasn't in this square, how do you trust engineering developments, what would they say?
When they were reconstructing the I-85 bridge,
one of the things that somebody commented on the radio, is it safe? They did it in such a hurry. Do they trust us?
Right. And I think that generally speaking, if you were to ask the broad civilian population who aren't professional engineers, maybe who are even engineers themselves, they'd say, I don't think about it. I've never thought about whether I should trust engineering developments. I mean,
I don't care.
Right. Best case, you get apathy. Worst case, you get indifference. Right. And I think, I'm sure that you've had some interaction with somebody who said, I don't trust that bridge. I'm not driving across it. Okay. What about the other 99.99999% of people? Right? I always like to think about it in terms of air travel. When I was giving this presentation, naturally, I flew to Philadelphia, and I thought that the bulk of everybody else who had been there probably had also flown to get there. So given that we know airplanes can fly themselves autonomously, we've known that for years. Everybody knows what autopilot is, right? Well, that was first demonstrated in 1914, over 100 years ago. I don't know the limitations on how well that system worked in, 100 and however many years ago, but lo and behold, it was first developed and first displayed 100 years ago as autopilot. We know that planes can land themselves. That's AutoLand. That was developed in 1937. I didn't know that. I knew about a system called the Instrument Landing System that's in a lot of big passenger aircraft that's capable of landing autonomously through through low visibility and a lot of cloud cover and things like that. But that was first displayed in 1937. Didn't know that. Well, we also know that planes can take off autonomously. I note here that the first vision-based demonstration was in 2020. Vision-based in this case means that there were sensors only on board the aircraft that were detecting when it was in the right place on the runway and when it was taxiing, et cetera, rather than it just doing a GPS pre-programmed thing or something along, basically an RC car. That was displayed in 2020 on some Airbus model that I can't remember the number of now because, as you know, they're all the same. But it all leads to a question, right? Planes can take off, can land, and can fly all by themselves. Would you get in the plane without a pilot in it? No. No one that I've asked that question to has said yes. Today, would you get in the plane without a pilot in it? And the answer is no. Okay. Fair. I'm not going to tell you that you're wrong. I wouldn't either. But what it leads to is that we as humans have limitations on what we call human fallibility, right? The only thing that we will do for certain is fail, right? We are imperfect creatures. We are naturally going to fail at whatever it may be that we're going to try to. Maybe catastrophically, maybe innocuously, but lo and behold, in the course of humanity, our mistakes are probably well more documented than our successes. And that's naturally because we have very many more failures than we do successes overall. There's good news in this, right? That means that we're forgiving creatures, that we're forgiving as a society, that we can mess up, and we can get over it within reason, right? We're not that way towards computers. We're not that way towards machines, whether they're smart or dumb. If it's a toaster, right, and all that it does is take in your little piece of bread and give you a slightly different piece of bread in a couple minutes, if it fails, you're angry, right? It's toast. It didn't even cost you anything. You forgot about it until it worked and maybe puffed out a little bit of smoke, right? Like we're very, very cruel. We're very, very impatient when it comes to machines. So our limitations on machine fallibility are very, very strict. In 2019, Carolyn Herzog, she's the executive, or she was at least at the time, the executive vice president, general counsel for the ARM Corporation. They produce computer chips is the broad definition. They posted a survey of 54 automotive industry experts. And what they found, and I'll quote this directly, in the survey they found that car makers expect that they'll have to prove that future self-driving vehicles are at least 10 times better in performance and AI decision-making to be acceptable by the public. 10 times! 10 times better. That is monumental. The reality is that if we had a car on the road today that was just as good as a human being, we wouldn't let it get on the road. We wouldn't. Because if it failed once, because we're so strict with these machines and their fallibility, we'd say, well, that thing's good for nothing. That's unforgivable. It needs to be better than a human. Whoa. Right? Like, we've had however many thousands of years of human interactions, interpersonal human interactions, and we've got to say, no, the first instance of this thing has to be better than a human being before I'll accept it. And that's crazy to me. But it leads to a further question. How many of you would get on a plane without a pilot on it if it were demonstrably 10 times safer than a human being? It has 10 times fewer in-flight problems, 10 times fewer crashes, 1/10 the number of crashes, I suppose is the right way to phrase that. And every time I've asked that question, someone said, okay, maybe I would. Right? It goes from this strict no, absolutely not, I wouldn't get on a plane without a pilot on it.
No, but
right.
Get on a plane with a pilot, even if the pilot doesn't do anything.
Sure. Right. Jesus was saying, yes.
I have a question about this. I'm 42 years analyzing automotive accidents. If I'm going to have to be as well aware of all the circumstances when the autonomous vehicle says, hey, I don't know what's wrong here, why have an autonomous vehicle? I haven't gained anything.
I don't disagree with that. You're not wrong. But I think that the true power in it comes with the mass deployment of this technology. You know, if tomorrow we had a vehicle that was cheap to make, that was 10 times better than a human being at autonomously driving, I mean, I imagine that cars could be traveling down I-85 at 70 miles an hour, bumper to bumper.
But they're still going to be mixed with drivers. How many years or decades?
Well, sure.
To complete the transfer. Look at all these.
I don't know. And I hope that, I'm so glad that you asked that question, right? Because in my mind, what that leads directly to is, well, where does the PE go? There's going to be perhaps decades where we have these mixed environments of autonomous systems in play at the same time as human beings. Where does the PE go? Yes?
Why don't we go ahead and use it in a restricted system? We've been using robots for decades. And as long as it's a restricted system, nobody gets hurt.
Right.
But if they want to try and predict human behavior of the individual human behavior. And good luck with that one.
No, you're absolutely right. And I don't have a good answer for that. Yes?
This is probably going well off track, but the whole liability question. Insurance and who's at fault in an accident and that sort of thing, as long as there is a mixture of autonomous control equipment in their vehicles.
Yeah.
And I think that plays on Luther's controlled environment, closed environment point versus the open environment that all of these rollouts are trying to tackle.
Right. Yes.
Maybe initially we would have like express lanes. The autonomous driving would be in separate lanes, so you want to go bumper to bumper at 80 miles an hour, you get a car like that.
I think that's ultimately what would have to happen, because obviously we're not going to build new roads. We haven't built new roads today. We're not going to build new roads just because we got AI driving them now. That all leads to a discussion of AI development and trust. And I put trust in quotes here. Yes, Jesus.
Before you get into trust, I think another big, it's just resistance to change, right? We can't change.
Sure. I mean, it's interesting though, right? Because I think that if I had a self-driving car that was, we'll call it demonstrably 10 times safer than a human driver, I would live out in Kentucky, and my commute would be 4 hours a day, and I'd just take a little nap in the back seat. You know, I'd buy 100 acres wherever I could, and I'd be happy with it. My commute would just be when I would sleep. I'd sleep 4 hours in the morning and 4 hours in the afternoon on the way to and from work. But like, most people wouldn't, right? Right.
What you are is a robot.
Right.
So that's discussions of physical safety and trust. How about a different kind of physical safety? Would you trust an AI to review legal contracts that involve money?
Right. I just saw a story in the news recently of a lawyer in, I don't remember which state, but somewhere in the U.S. that got in trouble for basically sourcing ChatGPT to draw up his legal argument, and ChatGPT created fake cases. Fake cases that weren't or that actually weren't legal precedent. Manhattan?
Yes. And then a judge in Texas is now making all the lawyers sign a paper that says if they use ChatGPT, they will physically check all of the
Right. And It sounds to me like that's what a professional engineer could do. Well, for engineering, not for law, perhaps.
It's on the Reuters site.
Right. So trust, capital T trust in quotes, right? What does it mean? What does it mean to trust an AI? And ultimately, like, if I ask my phone to set an alarm, I trust that it's done that. I don't double check it on a day-to-day basis. Am I going to get bit by it one day? Sure, probably. But ultimately, I'll trust it again because it's low consequence, right? If it fails, bummer. I'm a little bit late to work. A self-driving car can't fail in a little way, right? If it fails, it's in a catastrophic way, perhaps. As we sort of talked about at the beginning of this hour, we give AI a bad rap. We villainize it. Maybe in the same way that we villainize our toaster when it burns our toast, right? I think it's very easy to talk about how to use AI to make these developments, how to make these technologies that are unbelievably powerful. But it's very difficult to have a similar conversation of, well, how do we make it so that it's trustworthy? And maybe again, you just normalize it, and that may be what it is.
Just an observation.
Sure.
If AI is introduced as test automation or automation of factory plants, it's well received. But if it's introduced as something that's deceptive or something that can be used to foil a process, ethically wrong, then it's something else.
Of course.
It's kind of like introducing the electric chair was used to demonstrate electricity, we'd be lighting candles.
Absolutely. I'm sure that all of us that are professional engineers or perhaps engineers in training have looked at the NSPE Code of Ethics and we reference it on a routine basis, right? Everybody shake their heads. NSPEs were charged with nurturing relationships of trust, right? We can't exist without the public trusting us. Similarly, the public can't benefit from the works that we provide without trusting us. So I asked the question, what role must a PE take in order to certify designs that are generated in part or in whole by intelligent systems? I think that's an easy question to ask. That's an easy question to sort of provide an answer to, right? Is there any difference between me using AI to design a bridge and then I review all the plans and put my stamp on it versus having some dingus EIT do the same thing, right? Like, ultimately, they're probably just techniques. They're just tools in the tool bag that you can pull out whenever you like. And ultimately, you have to know the tools, right? Like, and when a carpenter takes his thumb off with the saw, I don't go, "That stupid saw." I go, "Oh, come on, man! What are you doing? There's safety that you got to follow. There's things that you got to do." However, the second question: what role must the PE take in order to certify intelligent systems themselves? I don't know the answer to that. We're talking self-driving cars, right? If professional engineers operated on the federal level, what role would a PE take in certifying the self-driving car, the Toyota AI, right? I don't know what that means. I don't know what that looks like. I have no idea how much process would be involved in that. How do you prove demonstrably that it is 10 times safer? Do you put it in front of 10 schools and see how many times it hits a kid? Whew, I don't like that idea. Yes?
Same problem we have today. I have to depend on my computer to do the calculations, although I put the formulas in and parameters put in, and I don't know the right calculations. Or do we find out when bridge fails? Oops.
Right, and I've seen certain PE communities say I'm assuming some of the more senior engineers, I'll call them, are saying that they still do their calculations by hand, and I go, well, that good. If you're verifying it with pen and paper, good. I appreciate that. As somebody that does occasionally use a bridge, I appreciate the thought that somebody has actually spot checked at least a handful of these calculations. I hope that we're not designing bridges today entirely by hand. I hope. As a taxpayer, I hope that's not the case. As an engineer, I hope that's not the case. As someone that understands human behavior and had a whole slide on human fallibility, I hope that isn't the case.
Remember the Hubble Space Telescope?
Yeah?
All it takes is one number.
Mm-hmm.
One little number.
So I have the the plug for my software that totally exists and all of you should definitely buy, the Halliwell Bridge Designer. All you do is put in your requirements and sometime later, poof, it spits out a bridge that fits in that exact criteria, right? How do you stamp that? I don't know. Maybe it is just a matter of spot checking a few of the calculations. Maybe you componentize it and see if the design somewhat matches up with what your expectations are. Maybe it's to within 5% and you go, okay, yeah, that's a good bridge. Maybe there's a few things that you need to change along the way. Great. Ultimately, in my mind, maybe it doesn't differ that much from any other design method. If you had this perfect application that all you had to do is input your input parameters and out comes a bridge, I mean, that's maybe drawing a bigger black box around the standard engineering process that's involved in designing a bridge. I'm not a bridge designer, so I can't really say. And ultimately, how does the public at large know to trust engineering designs today? And does the public at large ask or care about what methods were used to generate the design?
Typically they don't.
Absolutely.
The failure, they don't ask those questions.
Of course.
They trust us to ask those questions.
Right.
So that they don't have.
Right. Well, again, if we operated at the federal level, right? If we operated at the state level, how many times have you ever been to a city hall meeting where they were talking about a roadway and asking if the public approved the designs that were used for the roadway? Not how it's going to affect traffic, not, people are going to have to drive through my neighborhood, but no, I mean, they weren't audited for which design methods we're going to use. They don't. Go ahead, Mitch.
I'm involved in a insurance case now. May turn to litigation, but it's regarding the geographic location of some property lines, and there was a computer. Some settings were missed. Was input incorrectly and caused property lines to shift datas, which was about 6 feet for an entire 3-mile road widening database, and then all the acquisitions were improperly done, and there's having to go back and do a lot of rework. The problem was caused by the computer.
Yeah.
At least in the engineer's claim. But the insurance company says computers don't cause problems.
Right. The computer didn't send us the plans. Right?
And I don't see that changing anytime very soon, but it's a matter of concern.
Absolutely.
Where does this evolve in the next decade and even sooner than that?
Absolutely. And this, in the research that I did throughout the generation of this slide, I think that I boiled it down to these 3 points. Ultimately, because the PE trusts the design by ethically applying their seal, and the public trusts PEs, the public trusts the design. Whether it's an implicit trust, whether they even need to think about it, it's a transitive property. The PE acts ethically. The PE trust, or the public trusts the PE, and therefore the public doesn't care what the PE does, effectively. The public gets to not care. What a privilege that is. Right? Imagine if every single time we tried to do any public work, the public were distrustful of the actions that we were taking. We've earned this reputation as professional engineers. We've earned this reputation as trustworthy, as ethical. Absolutely. And I think that more or less brings me to the end of my presentation. I have some sources here. I'm more than willing to distribute these slides to anybody that wants them. And if you want these sources emailed to you, by all means. But that's it. That's my time. Thank you, folks.
How should we request that?
JP, if you send them to me, I will attach them with the PDH email so everybody gets it. If you don't want it, you can trash it. But I think that would be the easiest administrative way to get it out.
Sure. Great idea, Jim.
All right, JP. Very, very interesting presentation.
Thank you.
We really appreciate it. This is a small token of our appreciation. Thank you so much.
Wonderful. I love that. Thank you, Jesus.
All right, folks, make sure that a couple of things. That you signed in.
We hope you enjoyed this presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.